Hello everyone, welcome to this lecture. In the previous lecture we studied excitation of a structure using impact hammer. The excitation will cause structure to respond, and then the question is that how do you measure the response of the structure. So in this lecture today we are going to talk about how to measure response, what response parameter should be used, and we are going to talk about accelerometers for response measurement. Therefore the topic today is response measurement. A brief outline of the lecture is as follows. First we will look at what parameter of response should be measured. Then we will look at why piezoelectric accelerometers are widely used for response measurement and model testing. Then we will look at what is seismic pickup, and then the piezoelectric accelerometers. Then we will look at what are charge amplifiers, what are IEPE or ICP types of piezoelectric accelerometers, then what are the mounting methods for accelerometers, and selection of the accelerometers for model testing. And at the end briefly we will talk about laser Doppler vibrometer. So the first point we are going to talk about today is selection of response parameter. So the response of a structure can be described in terms of displacement, velocity and acceleration, right. So we can have response description in terms of displacement, velocity or acceleration. So the question is which one of these parameters should be measured, because if we measure any one of them, the other two can be obtained by the process of differentiation or integration. For example, if we have a record of displacement, then the velocity and acceleration can be obtained by differentiating the displacement once or twice respectively. Similarly, if we have the acceleration signal, then we can obtain in principle the velocity and displacement of the response by integrating the acceleration signal once or twice respectively. So which parameter should be measured? So let us look at a typical spectrum of displacement, velocity and acceleration when a structure is subjected to random excitation. Okay. So let us look at the frequency spectrum of each of them. So the displacement spectrum representing it by x as a function of omega may typically look like this. So we may have this kind of behavior. If we look at the velocity magnitude of the velocity as a function of omega may look like this, something like this, right. And then if we look at the acceleration, let us represent it by a as a function of omega, then the acceleration would look something like this, right. So what we observe, let us look at the displacement first. So what we see is that in the low frequency range the displacement is high, right, but as the frequency increases the displacement becomes lower and lower, because at higher frequency structure finds it difficult to respond with a higher displacement, and that is why the displacement is lower in the high frequency range. So therefore the displacement is low in the high frequency range. So that is one observation. So because of this what may happen is that the signal to noise ratio may not be good in the high frequency range, because always there is some random measurement noise, a small measurement noise that might be present in the measured signal, and therefore the signal to noise ratio would suffer in the high frequency range. So that is one reason why displacement may not be a good parameter for measurement over the wide frequency range. The other thing we see is that in the low frequency range displacement is high, while in the high frequency range the displacement is low. So, it means not only high displacement amplitudes, but also low displacement amplitudes are there which need to be measured, and therefore, the dynamic range of the response, dynamic range of the displacement response is high. Okay. So, the dynamic range of the displacement response is high. Okay. So, which basically means that the measurement system that we use to measure displacement should have equal or more dynamic range. So, measuring displacement therefore would require a higher dynamic range. Okay. So, these are the two reasons which basically go against using displacement as a parameter of response measurement, right. Similarly, if we look at the acceleration, what we see is that in the low frequency range the acceleration amplitudes are small, because the acceleration is proportional to square of the frequency. So, in the low frequency range the frequency is small and hence the acceleration amplitude is also small. But as the frequency increases, the acceleration amplitude becomes higher and higher simply because the frequency is increasing. So, here also what we see that the acceleration is small in the low frequency range. Therefore, in the low frequency range the signal to noise ratio of the acceleration signal may not be good, right. So, that is one point against acceleration measurement. And also as we saw for the displacement response, for acceleration response also the dynamic range of response is pretty high, right, because in the high frequency range the acceleration is very high, but in the low frequency range it is low. So, it means the signal not only has low levels of acceleration components, but also has components with high levels of acceleration, is not it. So, we have low and high levels of acceleration to be measured, and therefore, the dynamic range of measurement system also should be somewhat more than this dynamic range of the acceleration response, right. So, therefore, here also we can say that the dynamic range of the acceleration response is high, correct. What about velocity? So, we see that the velocity amplitude is by and large uniform when we go from low to high frequency range, right. So, the velocity is largely uniform, right, from low to high frequency range, correct. So, because the velocity is basically proportional to displacement and also frequency, right, and therefore, in the low frequency range where displacement is high, but velocity frequency is low, still the velocity amplitude can be substantial, and in the high frequency range where the displacement amplitude is small, but frequency is high, again the velocity amplitude can be substantial or significant, and that is why the velocity amplitude is largely uniform over the whole frequency range, and therefore, the not only the signal to noise ratio should be reasonably good over the whole frequency range, but also the dynamic range of velocity response is small, right, it is smaller than that of the displacement and acceleration response, right. So, we can say that the dynamic range of the velocity response is smaller than the displacement and acceleration response, and therefore, we can have a measurement system with a smaller dynamic range and we can still do a good velocity measurement. So, that is the advantage of velocity response. So, from this discussion we see that the velocity response basically is a preferred parameter for response measurement, right. So, we say that velocity is the preferred parameter of response, right, based on signal to noise ratio and dynamic range requirements, correct. So, based on these conditions the velocity appears to be a preferred parameter, in fact is the preferred parameter of response measurement. However, there are some other considerations also which need to be taken into account while deciding that which parameter should be measured, especially the characteristics of transducers which need to be used, right, for measuring the response. They also affect, influence the choice of the parameter that should be measured. Therefore, we see that although the velocity is the preferred parameter of response measurement, but in practice accelerometers are widely used for response measurement. That is, instead of velocity we measure acceleration. Okay. So, let us see that why accelerometers are used in practice for response measurement, and specifically we use piezoelectric accelerometers. So, why piezoelectric accelerometers are used for response measurement. So, for vibration measurement and for model testing, piezoelectric accelerometers are widely used. So, that is because it has favorable characteristics for vibration and measurement and model testing. And what are those favorable characteristics? The first characteristic is that it has low weight. Okay, it has low weight or mass. So, because for measurement we will have to mount the accelerometer on the structure, right. So, it will cause mass loading of the structure, right. The mass of the accelerometer may change the dynamic characteristics of the structure and may affect the dynamic response, and higher the mass, higher is going to be this deviation or this change. And that is why for acceleration measurement we need to have transducers which have as small mass as possible, and accelerometers basically have small mass, and therefore they are preferable, and that is one of the important favorable characteristics of accelerometers. Other is that they have a wide frequency range, right. So, so accelerometers can be used for measurement over a wide frequency range. So, in practice often the signals have wide frequency range, and therefore accelerometers are suitable for those measurements. They also have a wide dynamic range, correct. So, the signal amplitudes of low value as well as high values can be measured. So, they have a wide dynamic range. And the other thing is that the integration needs to be carried out. To obtain displacement and velocity, right. So, if we have measured acceleration, then the displacement and velocity can be obtained by process of integration. So, in practice the signals often have small random measurement noise, and let us say if we measure displacement, then we will have to differentiate the signal in order to obtain the velocity and acceleration, right. Of course, for acceleration we need to carry out differentiation twice. So, the process of differentiation is very sensitive to noise. Okay. So, presence of noise may introduce a large error in the differentiation, in the differentiated quantity, and therefore the differentiation of the signal is actually not preferred for obtaining the required parameters. But the integration is not sensitive so much to the noise, and that is why from this aspect also the obtaining displacement and velocity from acceleration is a more preferred alternative than obtaining the acceleration and velocity from displacement through the process of differentiation. So, after this we are going to look at piezoelectric accelerometer, and the principle of working of piezoelectric accelerometer is based on seismic pickup, and that is why we are going to first look at the basic theory of seismic pickup. So, what is a seismic pickup? let us try to make a sketch of it. So, so this seismic pickup has a seismic mass like this, and then there is a spring and dashpot. Okay. So, this is seismic mass, this is stiffness, and this is damping. So, this is the casing of the seismic pickup, right, and this is seismic mass, right. So, this is nothing but essentially a single degree of freedom spring mass dashpot system inside a casing, and this pickup is then mounted on the surface whose vibration we want to measure. So, let us say we have this surface here whose vibration we want to measure like this. And then a stud is used to secure the seismic pickup to the surface in this manner. Okay. Let us say the velocity of vibration of this surface is, say, y of t equal to, let us say it is undergoing a harmonic vibration, say sine omega t. So, let us represent the vibration of the seismic mass by x. So, let us write the equation of motion for the seismic mass, that would be mx double dot is equal to minus k x minus y minus c x dot minus y dot. Let us define now the relative displacement of the seismic mass by quantity, let us say z, which is equal to the absolute displacement x minus the displacement of its base, which is y. So, if we substitute this relative displacement z into the equation of motion and we simplify it, we basically end up with this equation mz double dot plus cz dot plus kz is equal to m omega square y naught sin omega t. So, this is the equation we get. So, here basically the seismic mass is essentially being subjected to a base excitation, right, y of t, and z is the relative displacement of the seismic mass. And if we solve this differential equation and obtain the steady state response, and if the steady state response is given by, let us say, z of t is equal to z naught sin omega t minus phi, where omega is the frequency of the vibration and phi is the phase angle of the response. Then we see that the z naught upon y naught it is equal to omega upon omega n square divided by 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square and then square root of this. So, this is basically the ratio of the steady state amplitude of the seismic mass and amplitude of the base excitation. And if we plot this basically response, then it looks something like this. So, if you plot, say here z naught upon y naught as a function of omega upon omega n, right, then this looks something like this. For a particular value of zeta we are plotting this, and something like this, and this basically here this is 1, okay, and the frequency here is somewhat is actually 1, right. So therefore, what we see from this plot, let us take the case when let us take case A where omega upon omega n is much more than 1. So here omega n is the natural frequency of the seismic mass or seismic I mean pickup, natural frequency of seismic pickup, and zeta is the damping factor of the seismic pickup. So in the range omega more than omega 1, it can be easily seen that z naught upon y naught is approximately equal to 1, right, which means that z naught is approximately equal to y naught. So this means that the relative displacement of the seismic mass is approximately equal to the amplitude of vibration of the surface, right, which we want to measure, correct. So if we want to measure if we want to know the amplitude of vibration of the surface, then we should measure the relative displacement of the seismic mass. That would basically be the be nothing but the same will be the estimate of the amplitude of the vibrating surface, and therefore this pickup will act like a displacement pickup, okay, if we measure the relative displacement of the seismic mass, right, in the range omega upon omega n more than 1. So in the range omega more than omega n, the seismic pickup can be used as a displacement pickup. Means it can be used as a displacement transducer. Now for in practice, for example, if we want to measure the displacement, then the range of frequency, it should normally be covered from the low frequency range to high frequency range, right. So in order to measure vibrations with sufficient low frequency, the omega n therefore should be smaller than that lower limit of the frequency range. So therefore the omega n of the displacement pickup should be very small, correct. Omega n should be very small. Now since omega n of the displacement pickup has to be small, they are heavier, right, they have a higher mass, and therefore they cannot be used for measurement of displacement for low and medium size structures, because the mass loading otherwise will be significant. Similarly, this displacement pickup can be also used as a velocity pickup if we differentiate the output of the displacement pickup by using another transducer, right, and then that can be used as a velocity pickup. But then that will also again suffer from the same disadvantage that for low and medium structures, size structures, the mass loading will be significant, and hence they cannot be used, or they are not preferred for vibration measurement. Now for such structures, let us look at now another case, case B, let us call it, where now omega upon omega n is much less than 1, which basically means that omega is much less than omega n. So the equation therefore can be simplified as omega upon omega n square, correct, because the denominator now tends to 1 when omega upon omega n is less than 1, and therefore this also can be written as 1 upon omega n square, right, multiplied by omega square y naught. Now what is omega square y naught? Omega square y naught is nothing but the acceleration amplitude to be measured, right. And therefore, here the relative displacement Z naught is nothing but an estimate of the acceleration amplitude scaled by a factor 1 upon omega n square. So, therefore, if we measure the relative displacement of the seismic mass and if we scale it by omega n square, then that basically gives us the estimate of the acceleration amplitude. And therefore, for this frequency range omega upon omega n less than 1, the seismic pickup can be used as an accelerometer. It can be used for acceleration measurement. Therefore, for omega upon omega n less than 1, the seismic pickup can be used as an accelerometer. It can be used as an accelerometer. And in order to have a sufficiently wide enough frequency range, the omega n of the seismic pickup, it should be very large as compared to the upper limit of the frequency range. Therefore, the natural frequency of the seismic pickup should be high. Okay. And high natural frequency can be realized by having a smaller seismic mass and high stiffness, right, of the seismic system, right. And therefore, this basically makes the seismic pickup which are to be used for acceleration measurement to have lower mass or lower weight, okay. And that is why therefore, they can be used for acceleration measurement for low and medium size structures even, right, because they would not cause significant mass loading of the structure. Now we are going to talk about piezoelectric accelerometers. So we saw that to measure acceleration, we basically need to measure the relative displacement of the seismic mass, isn't it? And in piezoelectric accelerometers, a piezoelectric crystal or a piezoelectric disc is basically used to measure the relative displacement, okay, because then that can be scaled in order to obtain the acceleration amplitude. So let us sketch a piezoelectric accelerometer. So this is the surface on which the piezoelectric accelerometer is mounted to measure the vibration of the surface. Using a stud. Okay, of course, this is one way to mount the accelerometer. And then we have, so this is preloading spring, this is seismic mass, this is piezoelectric disc, right. and then we have these conductors which basically collect the electric charge developed on the piezoelectric crystal surfaces like this. Right, so here we get the output. Okay, so this is the basic arrangement of a piezoelectric exometer. So here we see that in the piezoelectric disc basically provides the stiffness and the damping associated with the seismic pickup, and therefore now when the this surface it vibrates, let us say with amplitude y of t is equal to y naught sin omega t, then this seismic mass it vibrates with amplitude x, right, and therefore what happens, the upper surface of the piezoelectric disc is subjected to displacement x, while its lower surface is subjected to displacement y, right, because the base of the piezoelectric exometer is also subjected to the vibratory motion y, right, and therefore what happens, the piezoelectric disc is subjected to a net displacement x minus y, that is z, and therefore the deformation of the piezoelectric disc is nothing but z, which is the relative displacement of the seismic mass. And because of that, what happens, the piezoelectric disc due to deformation it generates a proportional charge, electric charge, that is the property of piezoelectric materials, that is when they are deformed they generate charge proportional to the deformation, and that is basically called basically the piezoelectric effect. And then this charge therefore then if can be measured, then we can basically get a measurement of relative displacement z, right, because the constant of proportionality for the crystal would be known. So this is the basic principle of working of piezoelectric exometer. The relative displacement z is basically indirectly sensed by measuring the charge that is generated because of the deformation of the crystal, which is equal to the relative displacement z. Okay. Now here a preloading spring is also used. The preloading spring gives a sufficient initial compressive deformation in the disc, so that for the positive and negative displacements of the disc during vibration, for all the cases, for both the cases, the net deformation in the disc remains compressive. So therefore here the displacement z produces a charge q that is proportional to the relative displacement z. So this is electric charge and this is relative displacement of the seismic mass. So the piezoelectric disc is made from piezoelectric materials. And the common piezoelectric materials are quartz, then we have barium titanate, and lead zirconate. So therefore here the output of the exometer is in terms of charge, right, and therefore these exometers are also referred as charge types of piezoelectric exometers. Okay. The output of the charge type of piezoelectric exometers cannot be directly measured by connecting them to any voltage measuring device, okay, and what we require is a charge amplifier. So, the output, the charge output, right, is a high impedance signal. Charge output of a piezoelectric exometer is a high impedance signal, and therefore, if we directly connect it to any voltage measuring device, then the signal will be severely loaded and the measurement we get will not be accurate, will not be a correct measurement, and that is why we can't directly measure the output of a piezoelectric charge type exometer directly. So, this needs to be converted to a low impedance signal, and charge amplifier basically is used for that purpose. Okay. So, charge amplifier converts the high impedance signal to a low impedance signal. Okay. And then that output then can be measured using a voltage measuring device. So, therefore, the output of the piezoelectric exometer is first fed to a charge amplifier, and then output of the charge amplifier is then measured, right, and that is in terms of proportionate voltage. So, we get the voltage output of the charge amplifier that is proportional to the acceleration of the surface. Then we have what are called as IEPE or ICP accelerometers. So, IEPE basically stands for Integrated Electronics Piezoelectric, which basically is standard for piezoelectric accelerometers with built-in electronics for amplification. So, these IEPE types of piezoelectric accelerometers, they have a built-in charge amplifier. Okay. So, a small IC which basically does the job of charge amplification, right, or works as a charge amplifier, is built into the transducer itself. So, no external charge amplifier is required. Okay. So, no external charge amplifier is required. So, that is the advantage of these types of accelerometers, right. They are easy and handy to use, and they are available commercially with several trade names, like for example ICP or Deltatron or Isotron, Piezotron. So, these are basically the trade names of commercially available IEPE types of piezoelectric accelerometers. So, these accelerometers therefore, the output is basically directly in terms of voltage signal, and that is why the sensitivity of these accelerometers is expressed in terms of millivolts per meter per second square, okay, or millivolts per g of acceleration, something like this. And for the charge type accelerometers, the sensitivity is in terms of picocoulomb per meter per second square or picocoulomb per g of acceleration. G basically is the 9.8 meters per second square. Now, what are different ways accelerometers can be mounted on the structure whose vibration is to be measured. So, let us look at mounting of accelerometers. So, the mounting basically refers to the method by which the accelerometer is secured to the structure, right, at the location where the vibration is to be measured. And the type of mounting would basically determine the contact stiffness of the connection between the accelerometer and the structure and would affect the usable frequency range. So let us look at some of the methods which are widely used for mounting of the accelerometer. So, one of the method is stud mounting. So, in this case the accelerometer is secured to the surface using a stud, right. So, let us say if this is the accelerometer and let us say this is the surface, then so this is the surface and now a stud is used. So, a hole is drilled in the surface and threads are cut into that hole and then a stud is used to connect the accelerometer to the surface like this. So, stud mounting provides a very firm connection attachment of the accelerometer and the surface, and that is why it provides the maximum usable frequency range among all the mounting methods. But this also requires a hole to be drilled and tapped into the surface, and wherever such a damage to the surface is not acceptable, then this mounting method cannot be used. Then we have magnetic mounting. So, let us call this 1. So, this is method 1, then we have 2. So, in magnetic mounting a magnetic base is used, right, over which the accelerometer is mounted. Therefore, we have a magnetic base like this, okay, and then we have the accelerometer. Like this. So, this is the magnetic base. So, for using magnetic mounting, the surface or the structure should be ferromagnetic, but the contact stiffness as compared to stud mounting is little bit lower, and therefore, the usable frequency range with this mounting is smaller than the usual frequency range in case of stud mounting. Now we have adhesive mounting. So, in adhesive mounting a thin layer of adhesive is used, okay, to glue the accelerometer to the surface. So, this is the thin layer of the adhesive like this, and then we have the accelerometer like this. Right. So, this is so the usual frequency range obtained using adhesive layer mounting is smaller than that obtained with the magnetic mounting. We can also use what is called as cementing stud mounting. So, in case of adhesive mounting, if the accelerometer has to be removed, then the bond because of the adhesive layer has to be broken, right, then only the accelerometer can be removed. So, in case of cementing stud, the adhesive layer is used to cement a stud on the surface. Like this. So, we have now a cementing stud here like this, which is glued to the surface, right, and then the accelerometer then can be secured onto the cementing stud like this. Okay, so this is cementing stud and this is adhesive, right. So it becomes easy to remove the accelerometer whenever required. Okay. So, but again the usual frequency range using cementing stud mounting is smaller than that obtained using the adhesive mounting. Let us now talk about how to select an accelerometer for model testing. Accelerometer selection. So, there are several considerations which need to be looked into while choosing an accelerometer, right, for vibration measurement and for model testing. So, the first consideration could be regarding whether we want a uniaxial or triaxial accelerometer. Okay. So, if the measurement of acceleration has to be done only in one direction, okay, then the uniaxial accelerometer can be used. But if you want measurement of acceleration in 3 mutually perpendicular directions at any location, then triaxial accelerometer should be used. Okay. So, depending upon the requirement of measurement, either a uniaxial or a triaxial accelerometer should be used. Then we also should decide whether we want to have a charge type or IEPE or ICP type of accelerometers. So, charge type accelerometers would require a separate charge amplifier, external charge amplifier, while IEPE type accelerometers do not require an external charge amplifier. However, if vibration has to be measured under elevated temperatures, right, the surface on which let us say the accelerometer is to be mounted has a elevated or high temperature, then the IEPE or ICP type of accelerometers cannot be used on such surfaces because the built-in that amplifier may get damaged. So, under such condition, the charge type accelerometers should be preferred. Then the design. So, design basically refers to how the piezoelectric crystal is arranged with respect to the specific mass. Okay. So, so there are several designs available like compression, then we have shear design, we have flexure design. Okay. So, let us look at compression and shear designs. So, in the compression design, the piezoelectric crystal or the disc is under compression. So, let us quickly sketch it. Okay, and let us sketch the shear design. Okay. So, let us say this is the surface on which it is mounted, whose vibration is to be measured. Okay. So, this both surfaces they are vibrating. So, here this is the direction of polarization. Okay. So, therefore, this is compression design and this is shear design. So, in the compression design, the piezoelectric crystal, which is shown by red, right, piezo crystal, right, here also this is piezo crystal, right. In the compression design, there is a compressive load when the the structure vibrates, and when the seismic mass shown by green color, when that also displaces, then the piezoelectric crystal is subjected to a compressive deformation, right. But in case of the shear design, the crystals are arranged such that when the structure vibrates, then the seismic mass they move such that the crystal is subjected to a shear load, right. We can see that it is subjected to shear load, and the charge is developed on the surfaces which are subjected to shear, which are basically the contact surface between the piezoelectric crystal and the seismic mass. So, now what happens, there is also something called pyroelectric effect, which basically leads to generation of electric charge if there is a change in temperature. So, these piezoelectric crystals they will also generate charge if there is a change in temperature, and this charge that is developed, it is on surfaces which are perpendicular to the direction of polarization of the crystal. So, in case of compression design, the charge that is developed due to pyroelectric effect is developed on the same surfaces on which the charge also develops due to deformation of the crystal. So, in case of compression design, the charge is developed on this surface, right. So, charge due to deformation and charge due to pyroelectric effect. So, both these charges are developing on the same surface, and therefore, the charge signal gets corrupted because of the pyroelectric effect, because of the temperature change. But in case of shear design, the charge due to deformation is developed on this surface. Okay. So, the charge due to deformation, shear deformation, developed on this surface, while the charge due to pyroelectric effect is developed on a surface which is perpendicular. So, this here the charge due to pyroelectric effect. Therefore, the exometers based on shear design have the advantage that their signal is more accurate, okay, because it is not corrupted due to charge development due to temperature changes. Another important consideration is the weight. Okay, the weight of the exometer should be as small as possible, right, because it is going to basically do the mass loading of the structure and would lead to inaccuracies in the measurement. So, therefore, we have the exometers like something like say 40 gram, 50 gram and so on. So, these are the general purpose exometers. So, they can be used on structures which are big enough in size. But if we have structures where we want to make measurements which are lighter, which are small in size, like for example a computer disk drive, then we can't use an exometer weighing something like 40 gram and 50 gram, right. So, there are exometers called miniature exometers. Okay, like weighing something like 2 gram, 3 gram and so on. So, such exometers have very small mass and therefore, they can be used in such applications. Then another factor is sensitivity. So, generally exometers with high sensitivity should be preferred, because even the low levels of excitation can be used, and with high sensitivity for low levels of excitation also a good signal to noise ratio can be realized. However, another important consideration is the dynamic range of measurement that is available, right, to perform a given measurement. If the excitations that are encountered, they are not only low but also very high, right, then using a very high sensitivity exometer would be fine for low levels of excitation, but with high levels of excitation the input end of the analyzer will be loaded, will be overloaded, and therefore the high sensitivity exometer for such signals may not be good. Therefore, while choosing exometers, we should choose exometers with adequate sensitivity, but ensuring that the dynamic range of response can be measured with the available measurement system. Another related issue is that exometers with high sensitivity generally have higher mass. Exometers with higher sensitivity have higher mass, and higher mass basically is associated with lower frequency range of the exometer. Additionally, higher mass is also responsible for higher mass loading. So, these are some contradictory effects, right. So, another important characteristic is frequency range. Okay. So, let us look at the frequency response of a typical exometer. So, let us plot output of the exometer divided by the input in terms of dB, right. So, this curve is something like this. Okay. So, this is the frequency, okay, and this is the, so frequency range of the exometer is the range over which the frequency response of the exometer, right, that is the output upon input of the exometer is linear, and from this graph we see that it is linear over this range, right. So, this is the useful frequency range. Okay, of the exometer, and therefore, and so this peak here is nothing but the resonance. So, this is the resonance of the exometer, and this frequency is nothing but the natural frequency of the exometer. This is the natural frequency of the exometer. So, therefore, the upper cutoff of the frequency range, let us call it FU. So, that is basically limited by the natural frequency of the exometer. So, it is seen that the exometer also cannot be used for measuring static excitation, right, or excitation with very low frequency, and that is why the in the low frequency range also, for very low frequency range, exometer cannot be used for excitation measurement, and therefore, that determines the lower cutoff frequency of the exometer. And this lower cutoff frequency basically depends upon the time constant of the amplifier circuit. That time constant basically determines the lower cutoff frequency of the exometer. Another parameter is the dynamic range. So, dynamic range basically refers to the signal amplitude which can be measured, right. So, the frequency range refers to the range of frequencies, while the dynamic range refers to the signal amplitude, not the signal frequency. And typically, accelerometers have very high dynamic range, right. For example, a typical accelerometer, the lowest acceleration level that can be measured is something like say 2 into 10 to the power minus 3 meters per second square, right. And the highest acceleration level that can be measured is 2 into 10 to the power 4 meters per second square. So, above this range and above this level, the response may become non-linear. So, this basically is the typical value of the highest acceleration level that can be measured using piezoelectric accelerometer. So, this basically corresponds to a dynamic range of around 140 decibels. So, that is a very pretty high dynamic range. And therefore, the accelerometer that is chosen should be such that the accelerations encountered in practice which we want to measure they fall within this dynamic range. Another relevant parameter is transverse sensitivity. Okay. So, transverse sensitivity is basically let us sketch the accelerometer first. Right. So, this is the main axis of the accelerometer. Okay. This is the main axis of the accelerometer. But if there is also vibration perpendicular to this, okay. So, if there is a vibration perpendicular to this, then the accelerometer the piezoelectric crystal generates some charge due to this acceleration also, right, and that is basically referred as the transverse sensitivity. So, the amount of charge generated in the direction perpendicular to the main axis, right, due to vibration in that direction is referred as the transverse sensitivity. So, this transverse sensitivity should be small, right, because it is basically going to corrupt the charge signal due to acceleration in the direction of the main axis, and it basically will make our measurement inaccurate, right. So, the transverse sensitivity should be small. Right, should be, and generally it should be less than say 5%, right. So, these are basically the various factors which should be taken into account while choosing an accelerometer. Now, we are going to briefly talk about another technique of vibration measurement, which is based on laser Doppler vibrometer. Often abbreviated as LDV. So, it is seen that when light is incident on a moving surface, right, then the frequency of the reflected light undergoes change, right, and that change is proportional to the velocity of the vibrating surface, and this change is referred as Doppler shift, right, and therefore, if we can measure this Doppler shift, then we can estimate the velocity of the vibrating surface. Okay. So, this is the basic principle of laser Doppler vibrometer. So, let us say if we have this surface which is vibrating, right, with velocity v, and if light is incident on this surface like this, then this light is reflected. Okay. So, if f is the frequency of the light, then what happens? The frequency of the reflected light will be f plus delta f, right, and this delta f is proportional to the velocity, right, and this delta f is basically referred as Doppler shift. Okay. So therefore, if Doppler shift can be measured, then the velocity of the surface can be estimated, and the velocity of course we get will be in the direction of the incident light. In that direction the component of the velocity can be determined. So in the commercially available Doppler laser Doppler vibrometer, the phenomenon of interference is used to determine this Doppler shift. Because the frequency of the light is very large, right, and generally the velocities which are encountered, which we generally want to measure, they are small, the Doppler shift is much small, right, and therefore a direct measurement of the Doppler shift is difficult, right, and it will not be accurate, and that is why an indirect technique of measuring the Doppler shift is basically used. So therefore a direct measurement of Doppler shift, that is delta f, is difficult because the frequency of the light is very high and the velocities that are there are small, resulting into small Doppler shifts, and therefore the phenomenon of interference is used to measure Doppler shift. So in this the reflected beam is made to interfere with the parent beam, right. The parent beam has not gone any Doppler shift, while the reflected beam has undergone Doppler shift, and these two beams, when they basically are interfered through an interferometer, then the result of the interference basically helps to determine the Doppler shift. So that is basically the idea used in the commercially available laser Doppler vibrometers to determine the Doppler shift. And so there is also something called scanning laser Doppler vibrometer, right, scanning LDV. This scanning LDV is an extension of the single point LDV. So in scanning LDV, the light, that is basically the laser beam, is basically automatically moved from one test point to other test point, okay, using some control mirrors, okay, and therefore this helps to automate the process of measurement over a large number of points, and then therefore the vibration or the velocity can be measured at large number of points in a small length of time. There is also something called 3D SLDV. So this 3D SLDV has basically got 3 laser Doppler vibrometers or 3 SLDVs. They are mounted in space, right, and then they all direct their laser beams at a single point on the test surface, and they basically determine the velocity of the surface in 3 different directions, and from that the complete velocity vector at the point can be constructed. So 3D SLDV allows to measurement all the 3 components of velocities at a point, right. So what are the advantages of LDV? So as compared to exometer, what are the advantages of LDV? So one advantage is that it is a non-contact method of measurement. Okay, because here the light, that is the laser beam, is used through which the velocity is measured, and therefore it is a non-contact method, and while the exometer needs to be mounted on the surface, okay, so it is a contact based method, and that basically causes the mass loading of the structure on which the exometer is mounted. But in case of LDV, there is no mass loading effect, and therefore the measurements can be more accurate, right, and especially when the object or the system on which the vibration is to be measured is lighter, it is small in size, then this method will be more important and will be useful, right. Other advantage is that the measurement under harsh environments can be done. For example, if the temperature of the surface is high, then it would be difficult to use an exometer. But with this method, because there is no contact, the temperature of the surface does not cause any serious challenges, right. So, another advantage is that measurement from a large distance is possible, correct. So, even something like from 100 meters away also measurements can be done, because laser beam is a very coherent source of coherent beam, right. So, it can travel over a large distances. So, it is not ordinary light, right, and therefore, the measurement from a large distance is possible. So, this is also especially useful where the point is inaccessible. We cannot access the point so easily where the vibration is to be measured, right, but the laser beam, if it can reach to that point, then the vibration measurement can be taken at that point. So, there are some limitations. Right. So, first is that the surface has to be a polished surface, right, because the beam should reflect from that surface. So, the surface should be polished or smooth, right, and it should be reflective. Because ultimately the reflected beam has to be captured and analyzed. Okay. So, therefore, often some small reflective tape may need to be pasted. Okay. So, reflective tape may be required. Other requirement is that there should be a line of sight. Okay. So, the point must be visible, because then only the beam can reach there. So, that is one requirement. If the point is not under the line of sight, then measurement cannot be taken. Then sometimes if the surface is rough, then there is lot of diffusion of the incident light, and that basically leads to noise in the signal, right. So, that is often referred as speckle noise. So, sometimes the measurement may not be very good because of the speckle noise. In fact, another advantage of the LDV is that the size of the laser spot is very small, right, something like like 12 micrometers, the size of the laser spot, and therefore, the advantage is that the measurement precisely at the desired location can be taken. Okay. And also because of the small size of the laser spot, a very good spatial resolution on the surface can be obtained, okay, and large number of measurements can be taken so as to very accurately describe the vibration of the surface. So, in this way today we looked at the response measurement, we looked at how exometers can be used for response measurement, and we also looked at briefly the principle of LDV. Now, we stop here. Thank you.